This is Venus, the brightest natural object in our night sky after the moon, a planet almost exactly the size of Earth with a rocky surface and a thick atmosphere, a world that, by every early estimate, should have been a close cousin to our own. And yet, in all of human history, only a handful of photographs have ever been taken on its surface. Fewer than a dozen images. Every single one of them came from a single space program in a single decade, nearly half a century ago. Since 1982, no spacecraft has sent back a single photograph from the ground of Venus, not because we stopped trying, but because Venus, when we finally got there, turned out to be something no telescope, no model, and no theoretical framework had fully prepared us for. What those images show is real. The rocks, the light, the strange flat slabs extending to a hazy horizon, all of it captured by Soviet spacecraft under conditions that should, by engineering standards, have been impossible to survive. But what those images mean, and what they don't show, is where the story gets complicated. To understand why Venus surprised us, you have to understand what scientists genuinely believed about it before the space age, and why those beliefs were scientifically reasonable. Venus is perpetually wrapped in an unbroken cloud deck. No surface feature has ever been visible from Earth through an optical telescope. Not a mountain, not a sea, just clouds, all the way around, all the time. In the 18th century, Mikhail Lomonosov correctly deduced from a 1761 transit of Venus that the planet had a substantial atmosphere. Combined with its position only slightly closer to the Sun than Earth, this led to a logical inference. Venus probably had a warm, wet surface. By the early 20th century, the Swedish chemist Svante Arrhenius, the same scientist who first described the greenhouse effect on Earth, proposed that Venus was likely covered in swamps and dense tropical vegetation. This wasn't fringe speculation. It was the considered opinion of serious scientists working with the best available data. Popular culture ran with it. Science fiction depicted Venus as a jungle world, wet, warm, alive. That assumption held to varying degrees until 1956. That year, radio telescope observations detected unusually intense microwave emissions from Venus. Microwaves are associated with heat. The readings suggested a surface temperature not of tropical warmth, but of several hundred degrees Celsius. The debate continued until December 1962, when NASA's Mariner 2, the first successful interplanetary spacecraft flyby in history, measured Venus's thermal emissions directly. The result was unambiguous. Surface temperature, approximately 425 to 500 degrees Celsius. Hotter than Mercury, hot enough to melt lead, hot enough to destroy most electronics in minutes. The tropical Venus was dead. But what the surface actually looked like, what lay beneath those permanent clouds, remained completely unanswered. The Soviet Venera program began in 1961, and its early history is one of the most instructive sequences of iterative failure in space exploration, not because of poor engineering, but because Venus proved far more hostile than even the post-Mariner data had suggested. Early probes either lost contact en route or were crushed before reaching the surface. The problem was atmospheric pressure. Initial designs were built to handle around 10 atmospheres, 10 times Earth's sea level pressure. That seemed generous. It was not nearly enough. Venera 4, in 1967, became the first probe to enter another planet's atmosphere and transmit data in real time. As it descended on parachutes, temperature and pressure readings climbed at roughly 25 kilometers above the surface, still far from the ground. The probe failed. The pressure at that altitude alone had exceeded its design limits. The actual surface pressure of Venus, scientists now calculated, was close to 90 atmospheres, equivalent to being nearly a kilometer underwater. This forced a complete redesign. Future landers would need to be armored pressure vessels, built from titanium and high-temperature alloys. Every internal component would need to function at over 460 degrees Celsius, under crushing compression. Because no electronics could survive indefinitely in those conditions, each lander was designed with a thermal buffer, heat-absorbing material that would slowly warm through, giving the probe a finite window on the surface before internal temperatures rose past operating limits. Every Venera landing was a race against time, measured in minutes. Venera 7, in December 1970, became the first spacecraft in history to successfully land on another planet and transmit data from the surface. It sent back readings for 23 minutes before going silent. 465 degrees Celsius, 90 atmospheres. Venera 8, in 1972, survived 50 minutes and confirmed something important: that diffuse light was reaching the surface through the cloud layers. Photography was theoretically possible. The stage was set. Venera 9 landed on October 22, 1975. Veneras 13 and 14 followed in March 1982. Together with Venera 10, these 4 missions produced every surface photograph of Venus that exists. They are still the only ones ever taken. Venera 9 transmitted the first photographs ever taken on the surface of another planet. What they showed immediately surprised scientists. The surface was not a field of fine dust or smoothly eroded material, as many models had predicted for a planet with billions of years of chemical weathering. It was covered in angular fractured rock, sharp-edged slabs, and boulders that looked geologically fresh, not rounded, not ground down, broken. This suggested that erosion on Venus was slower than expected, or that the rocks were relatively young, possibly refreshed by recent volcanic activity. Either interpretation was significant. Venera 13 landed on March 1, 1982, and remains one of the most successful planetary surface missions in history. It survived 127 minutes on the surface, more than twice its design specification, and transmitted color panoramas showing flat, slab-like terrain of dark basaltic rock. The surface extended to a horizon obscured by atmospheric haze. The rocks had a layered appearance in places, though analysis confirmed them as volcanic in origin, shaped by ancient lava flows. No water, no dunes, no obvious signs of atmospheric precipitation. The surface looked dry and ancient, yet, paradoxically, unweathered. Venera 14 landed 4 days later at a different site, photographing smoother, more processed terrain, a different geological history, just a few hundred kilometers away. These 4 landing sites remain the only ground truth we have ever had for the surface of Venus, and they haven't been revisited since. If you've looked at the Venera images and noticed that everything appears in shades of orange, brown, and amber, that's not old cameras or degraded film. It is an accurate representation of what the Venusian surface actually looks like under Venusian lighting. The cloud deck of Venus begins at roughly 45 kilometers altitude and extends to about 70 kilometers. It is composed primarily of sulfuric acid droplets suspended in dense carbon dioxide. Below the clouds, the atmosphere is clear of particles, but it is still 90 times denser than Earth's air at sea level. As sunlight penetrates this atmosphere, shorter wavelengths, blues and violets, are scattered and absorbed preferentially. What reaches the surface is light that has been filtered through nearly 60 kilometers of thick, chemically reactive gas. The result, the surface is illuminated almost entirely by longer wavelengths, orange, amber, red. This is not fundamentally different from what happens on Earth at sunset, when sunlight travels a longer path through the atmosphere and the sky turns orange. On Venus, that effect is permanent and pervasive. The rocks in the Venera images are primarily basalt, dark gray under white light. They appear orange because that is the color of the light falling on them. Researchers who have processed the images using spectral correction to simulate neutral white light show the rocks in their expected dark gray-black tones. The Venera images are not distorted. They show Venus exactly as it is. Surface rocks, lit by the amber light of a sun, seen through 60 kilometers of sulfuric acid clouds. That is the Venusian day. In 2012, Russian planetary scientist Leonid Xanfomalidi published a paper in the journal Solar System Research proposing something unusual. He had spent time reanalyzing the original Venera 13 images and noticed what appeared to be changes in several objects between successive frames taken minutes apart. He identified a disc-shaped feature, a scorpion-like shape, and a flap-like protrusion, and asked whether their apparent movement could indicate living organisms. Xanfomalidi was not a tabloid writer. He was a respected planetary scientist at Moscow's Space Research Institute with a long career studying Venus. The paper was careful in its language, framed as a question, not a declaration. The scientific community's response was measured but clear. The interpretation was almost certainly incorrect for several well-grounded reasons. First, the Venusian surface environment is incompatible with any known biochemistry. At 465 degrees Celsius and 90 atmospheres of pressure in a chemically reactive sulfuric acid environment, the molecular structures that life depends on, proteins, nucleic acids, lipid membranes, cannot maintain their integrity. Second, the features Xanfomalidi identified were near the resolution limits of cameras that were scanning instruments operating in extreme conditions. The Venera images contain compression artifacts, scan line irregularities, and optical distortions, particularly near the edges of frames and near the lander structure itself. Third, the apparent movement between frames has straightforward explanations: changes in surface illumination, thermal expansion of the lander causing slight camera shifts, or debris disturbed during landing and still settling minutes later. These are expected behaviors of a spacecraft that has just landed on a hot, rocky surface. No subsequent analysis has endorsed Xanfomalidi's interpretation, but his reanalysis did do one useful thing. It drew renewed attention to how much we still don't understand about Venus's surface, and how long it has been since anyone looked. The Venera landers gave us ground truth at a handful of spots on a planet the size of Earth. NASA's Magellan spacecraft in the early 1990s mapped the entire surface by radar, giving us global topography. But radar tells you shape and elevation, not chemistry, not color, not texture. For that, you need to be there. And what we know from being there, combined with everything we've measured from orbit, includes several things that don't fit neatly into our models. One of the most persistent puzzles is the unidentified UV absorber in Venus's upper cloud layers. The cloud chemistry of Venus is reasonably well understood in broad terms. Sulfur dioxide cycles through the atmosphere, forms sulfuric acid droplets, descends, evaporates, and repeats. But within that cycle, there is a substance that has been absorbing ultraviolet light in the upper clouds since it was first detected by the Mariner missions in the 1970s. It absorbs roughly half of all solar energy that reaches that altitude. It produces the dark streaks and patches visible in UV images of Venus. And after decades of analysis, scientists have proposed several candidate chemicals, certain sulfur allotropes, iron chloride compounds, but none has been definitively confirmed. The absorber remains unidentified. In 2020, a paper in Nature Astronomy reported a potential detection of phosphine in Venus's atmosphere. Phosphine, one phosphorus atom bonded to 3 hydrogens, was notable because on Earth it is associated with biological processes and industrial production, and known Venusian chemistry should destroy it rapidly. The claim generated immediate scientific attention and immediate scrutiny. Subsequent reanalyses of the same data found the signal was weaker than initially reported, likely a calibration artifact. No corroborating signal has been found. The current consensus is that the detection was not real, but the episode illustrated something genuine. Venus's atmospheric chemistry still holds open questions. Then there is volcanism. Venus has more mapped volcanoes than any other planet in the solar system. The question of whether any are currently active has been debated for decades. In 2023, scientists reanalyzing Magellan radar data from the early 1990s found that a volcanic vent in the Maat Mons region appeared to have changed shape between 2 images taken 8 months apart, consistent with a lava flow or structural collapse during that window. The finding was published in the journal Science. This doesn't confirm real-time volcanic activity. The observation window was 8 months, and eruptions may be episodic. But it is strong evidence that geological activity has occurred on Venus within the recent past, which brings us to the question underlying all of this. Why is Venus the way it is? Venus and Earth are nearly identical in mass, size, composition, and solar distance. They formed from similar material at similar times. One has liquid water and life. The other has 460-degree temperatures, 90 atmospheres of pressure, and clouds of sulfuric acid. Understanding how Venus reached this state, what triggered the runaway greenhouse effect that baked it, is not only scientifically important, it's relevant to understanding Earth's own climate. The physics of the greenhouse effect is identical on both planets. The difference is one of degree. Several Venus missions are in development. NASA's Da Vinci will drop an atmospheric probe through the clouds, sampling chemistry layer by layer and photographing the surface from low altitude during descent. The European Space Agency's Envision will study Venus from orbit with multiple instrument suites. None of them include a surface camera. Landing on Venus, surviving long enough to photograph the ground, and transmitting those images back remains extraordinarily difficult. The Soviets did it briefly in the 1970s and 1980s. No one has managed it since. Those Venera images, amber-lit, slightly blurred, rocks on alien ground, under an alien sky, are among the strangest photographs ever taken, not because they show something inexplicable, but because of what it cost to take them. 15 years of iterative failure, redesign, and hard-won engineering progress, all of it to stand on the surface of the nearest planet to Earth and take a picture. What they show is real. The rocks are there. The light is that color. 460 degrees, 90 atmospheres. The genuine mysteries of Venus, the unidentified UV absorber, the active volcanism, the deep question of how a planet so like our own became so unlike it. These aren't mysteries for tabloid headlines. They're questions that require real missions, real instruments, and eventually more surface landers, more images, more time. The last photograph taken on the surface of Venus was transmitted on March 5th, 1982. Venera 14, 57 minutes on the ground before the heat won. That was more than 40 years ago. Venus is still there, still turning slowly in the wrong direction, still wrapped in its permanent clouds, still baking, still keeping most of its secrets. We haven't looked closely enough, but that is about to change.